All right, mathematicians, let's get started with section 4.4, Congruence Transformations. Our essential question, what conjectures can you make about a figure reflected in two lines? So our objectives, mathematicians will be able to identify congruent figures, describe congruence transformations, and use theorems about congruence transformations. All right, key point number 1, identifying congruent figures. Let's define congruent figures. It's figures that have the same size and shape. So let's look at these two sets of figures. The first set are representing congruent figures. That means all the corresponding angles are the same measure and all the corresponding sides are the same length. Whereas not congruent, you do not have corresponding angles congruent and you do not have corresponding sides the same length. So same size, same shape are congruent. And if they are different sizes or shapes, they are not congruent. All right, you can identify congruent figures in the coordinate plane by identifying the rigid motion or a composition of rigid motions that maps one of the figures onto the other. Let's recall, which of the transformations are rigid motions that we've learned so far? And that's translations, reflections, and rotations. All right, so let's take a look at these two examples. This first example, we have triangle ABC reflected across line ED, resulting in A prime, B prime, C prime, reflected one more time across this next line that's parallel to line ED, resulting in A double prime, B double prime, C double prime. Or we could have also a composition of rigid motions where we have triangle ABC reflected across line ED, resulting in this triangle, and then reflected across a line that intersects ED, also known as FD, resulting in A double prime, B double prime, C double prime. All right, so let's consider example 1. Identify any congruent figures in the coordinate plane and then explain. All right, so it looks like we've got two squares that look like they are similar by a translation. So either ABCD shifted left and then down on top of QPNR, or vice versa. So we can say that square ABCD maps on to square NPQR. And we have a rule for every XY coordinate that maps onto a new transformation would be following the rule of x minus 2, y minus 6. So it shifts 2 to the left and 6 down. So square ABCD and square NPQR are congruent. All right, next we can find a reflection. It looks like triangle EFGH and KLM are a reflection of each other. So we can say triangle KLM reflects and maps onto triangle EFG in the x-axis. And it follows the rule of all the xy coordinates, the y coordinates are opposite. So triangle EFG and triangle KLM are congruent. All right, next let's consider a rotation. So it looks like the remaining figures, IHJ and TUS, are a reflection of each other. So triangle STU is a rotation, is a 180-degree rotation of triangle HIJ about the origin. So we can follow the rule of both the x and y coordinates being opposite. So our explanation is that triangle HIJ and triangle STU are congruent. All right, let's consider key point number 2 on congruence transformations. It's another name for rigid motion because pre-image and image are congruent. Let's take a look at example number 2 where we can describe a congruence transformation that maps parallelogram ABCD to parallelogram EFGH. So we want to consider what transformations have to occur for this parallelogram to map onto this parallelogram. And it's definitely not a reflection across the line y equals negative x. and it doesn't appear to have been a rotation. So what about we reflect it across the y-axis and then maybe translate it? So you can make this consideration based on the orientation. They're not oriented the same way. So the only way we could get them to oriented the same way is to do a reflection. All right, so we can see by this illustration that the congruence transformation that maps parallelogram ABCD to parallelogram EFGH is a reflection in the y-axis, followed by a translation of 4 units down. So the reflection occurred to get our prime, and then it translates down 4 units. All right, let's consider key point number 3 using theorems about congruence transformations. So we have a reflections in parallel lines theorem. It states if lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. So let's take a look at our illustration here. Segment AB reflected across line K results in A prime B prime. And then A prime B prime reflected across a line parallel to K, called M, results in A double prime B double prime. And that distance, we know that we can also translate the original pre-image all the way over and get a result of that A double prime B double prime. So if A double prime is the image of A, then the following 2 statements are true. Segment A to A double prime is perpendicular to line K and line M. So that's what we see here. This line connecting A to A double prime is perpendicular to the 2 parallel lines. And then the distance from A to A double prime is twice the length of D, where D is the distance between the 2 lines. So our implied statement, 2 lines parallel, implies reflect each line and it equals a translation. All right, let's consider our next example using the reflections in parallel lines theorem. In the diagram, a reflection in line K maps segment GH to segment G prime H prime. A reflection in line M maps segment G prime H prime to segment G double prime H double prime. Also, the length from H to B is equal to 9, and the length from D to H double prime is equal to 4. So name any segments congruent to each of the segments, segment GH, HB, and GA. So we can say that the segment GH is congruent to segment G prime H prime, and GH is congruent to G double prime H double prime. HB is congruent to H prime B prime, just H prime B, and then segment GA is congruent to segment G prime A. Next question, does AC equal BD? Explain. Yes, AC does equal BD because segment G to G double prime and segment H to H double prime are perpendicular to both line K and M. So segment BD and segment AC are opposite sides of a rectangle. Next, what is the length of segment G to G double prime? By the properties of reflections, H prime B equals 9 and H prime to D equals 4. The reflections in parallel lines theorem implies that G to G double prime equals H to H double prime, which equals twice the length of B to D. So the length of segment G to G double prime is 2 times 9 plus 4, which equals 26 units. All right, let's consider our next key point, reflections in the intersecting lines theorem. So if lines K and M intersect at point P, then a reflection in line K followed by a reflection in line M is the same as a rotation about point P. So we can also say that the angle of rotation is 2 times x, where x is the measure of the acute or right angle formed by lines K and M. Let's take a look at our illustration here. So we can say that here's our pre-image AB, if I reflect it across line K, I get A prime, B prime, and then reflect it across M, I get A double prime, B double prime. That is the same as rotating segment AB about point P, resulting in an angle measure rotation that is twice the measurement of the angle formed by the two angles that intersect at point P. So our implied intersecting two lines at a point implies the reflection of each line equal to the rotation about the same point. All right, so let's take a look at example 4. In the diagram, the figure is reflected in the line K. The image is then reflected in line M. Describe a single transformation that maps figure F to figure F double prime. So as we mentioned in the previous theorem, a reflection in the line K will map a reflection followed by a reflection in the line M equals a rotation about point P. And the measure of the acute angle is 70 degrees. So by the reflections in the intersecting lines theorem, the angle of rotation is twice that measurement, resulting in a 140-degree rotation. So a single transformation that maps figure F to figure F double prime is a 140-degree rotation about point P. All right, and our final example is this real-world connection of an artist who uses what is called a tessellation to create the following art piece. A tessellation is a repeated geometric design that covers the plane with no gaps and no overlaps. So what transformations did the artist use when creating this tessellation? Well, we can see there were definitely potentially some translations and then some rotations. Question B, are the individual figures in the tessellation congruent? Explain your reasoning. Yes, all the figures could be created using one or more rigid transformations of an original shape. All right, that's all for this lesson. Be sure to bring any clarifying questions in and get ready to practice these skills. And I leave you with M.C. Escher's well-known artist for his transformational art. This is known as metamorphosis. Can you identify the transformation or transformations that were used?